Hi, it's me. We're going to talk about implicit differentiation today. And we're starting with this little warm-up. This is something that we've been doing, trying to find the equation of the line tangent to the curve at 3, 4. And so it begins with this circle. If you remember anything about circles from pre-calculus last year, x squared plus y squared equals 25 is a circle whose center is at the origin and it has a radius of 5. And so if I wanted to graph this in my graphing calculator, clearly it is not a function because it doesn't pass the vertical line test. And so, but I could solve this for y and take the square root of both sides and get this. And this is what I tried to do. And I only got the top half. There's two problems. Number one, it looks like a semicircle, and second of all, it looks like an ellipse. So you have to remember that at this step right here, it's actually plus or minus. You have to put it in as two separate pieces. Or what you could do is insert positive 1, negative 1. That's what we did last year. And so there's your graph, the full graph. And then if you do a zoom square, it squares up your screen, and now it should be a nice circle. Okay, that's beautiful. Almost as beautiful as the one I have graphed right there. And the point 3, 4 is on this curve. It's about here maybe. And we're trying to find the equation of the line that's tangent to this curve. So I really did only need the positive square root, but that's okay. I wanted you to see the whole picture. Since if I had done the point 3, negative 4, we would have needed the negative square root. So it is plus or minus the whole circle, but we're just going to use this. So how are we going to find the slope of this line? Well, we need to find the derivative. And so we need to see that this is, in fact, a chain rule. And there's a reason why implicit differentiation comes right after the chain rule, and you'll see in a minute. We're going to take the derivative of this, which would be, this is blob to the 1/2, so the derivative of that is 1/2 blob to the negative 1/2 times blob prime, which is negative 2x. I'm going to call in the cleaning lady, and she's going to say, hey, Renee, 1/2 times 2 is negative 1. And then the x is going to stay on top, and then this is going to go on the bottom. Remember, negative 1/2 power means two things. First, it means negative means put it downstairs to make it positive, and the 1/2 means square root. So here's my beautiful derivative. All right, that's y prime. And so if I'm trying to find the slope at the point 3, 4, I say, well, what's the derivative at 3? And if you plug 3 in there for x, you get negative 3 over 3 squared is 9, 25 minus 9 is 16, square root of 16 is 4. And there's our slope. So y equals negative 3/4 x plus b. And how do we find b again? Plug in 4 for y, 3 for x. Oh, this is going to be a fun problem. It's going to be 16/4 plus 9/4 equals b. So b is 25/4. So I'm hoping that this equation will be, let me see if I can put that on the screen there. Right, negative 3/4 x plus 25/4. And let's see. Oh, it's just beautiful. I love it. But sometimes we are unable to solve that equation explicitly for x, which is what we have been doing so far this whole year. We have always had our equations y strictly in terms of x. That's kind of called explicitly in terms of x. And then we take the derivative just in terms of x. But sometimes you are unable to solve an equation just for y strictly in terms of x. For example, we're going to do this example in just a minute. You might say subtract x cubed and then take a cube root, but you still have a y over there. So it's not easily solvable for y. So there's another way of doing this problem. So I want to move this up just a little bit. And I want to start out with the same problem we just had, but I want to do this implicitly without losing sight of the goal. We still are trying to find y prime. Just like up here, we found y prime, and y was strictly in terms of x, and then y prime was strictly in terms of x. But now we're trying to find y prime, but I want to use this notation. It gets a little cumbersome. The implicit differentiation is a little clunky, a little bulky, but it's okay. So what we're going to do here is we are going to go through and differentiate both sides of this equation in terms of x. With respect to x, I'm going to keep saying it like that. Take the derivative of this with respect to x. So I'm going to do the easy side first. The derivative of 25 with respect to x is 0. The derivative of x squared in terms of x is 2x. But here's where we have the problem. And again, there's a reason why this comes right after the chain rule, because implicit differentiation is actually doing the chain rule. And it's saying, okay, I'm going to put parentheses around that, and that's really y squared. The derivative of y squared in terms of y is 2y. But we're taking the derivative of y squared in terms of x. So it's really like blob squared, and so you say 2y, but then you need to multiply it by the derivative of the inner function, and the derivative of y in terms of x looks like that. You might want to stop and rewind and listen to what I just said. And let's not lose sight of the goal. This is where we're trying to end up. So we're trying to solve for that variable. So I'm going to subtract 2x from both sides, divide both sides by 2y, and then reduce it and clean it up, and I get that. So this is interesting because our derivative now has an x and a y in it, but we're not scared because remember what our point of interest is? 3, 4. We are given both an x and a y. Hey, our slope at the point 3, 4 is, well, plug in 3 for x and 4 for y, and you get negative 3/4. So let's do one more example. This video is not going to be very long. And here's the other example I promised. X cubed plus y cubed is 6xy. When you have choices, you could do it either way, but this way you do not know how to solve that for y. It's not like you can complete the square, that's y cubed. So you have to do this implicitly. And remember, the general rule is to take the derivative of both sides of the equation with respect to x and then solve for dy over dx. So the derivative of x cubed with respect to x is 3x squared. The derivative of y cubed with respect to x is really a chain rule now. And it's 3y squared times dy over dx. And I know what you're thinking because I've been teaching this for so long. You're thinking, so you're telling me, Mrs. Yake, that every time I have a y, I need that additional dy over dx? Yes. I used to let the kids just use y prime, and looking ahead, it's better for us to do this in terms of writing it as this quotient dy over dx. Okay, so the derivative of y cubed with respect to x is 3y squared times dy over dx. Now, we have a little bit of a problem on the right-hand side, and that is, let me get rid of this, this is messy, sorry. And that is that we have a product. There. And so we need the product rule. Now, well, yeah, we have a product, but we could take this 6 out front and deal with it later, and then do the product rule, but then we'll forget to distribute it through. So let's do this instead. Let's call 6x our first function and y our second function. So here we go. First times prime of the second. What is the derivative of y? The derivative of y in terms of y is 1. But the derivative of y in terms of x is dy over dx. Or you could say 1 times dy over dx. Plus the second times the prime of the first, which is just 6. And here comes the fun part. Because now you need to solve that equation for dy over dx. And this is, like I said, it gets kind of bulky. But I want you to notice something. Well, first I'm going to clean it up just a little bit. 3x squared plus 3y squared dy over dx equals 6x dy over dx plus 6y. Okay, I just had to clean that up a little bit. And now you really have 1, 2, 3, 4 terms. Whoops, sorry. You really have 4 terms in this equation. 2 of them have a dy over dx in them, and 2 of them do not. I was helping Max with this the other day, and I said, think about this problem right here. Okay, if you were trying to solve that equation for x, you would have to do 2 things first. You'd have to get all the x's on one side of the equation and all the non-x's on the other side of the equation, and then divide. And that's what we're going to do. And who says you have to get the x's on the left? You don't. You could get the x's on the right, subtract 9, okay? And then divide by 3. So keep that parallel problem in mind because that looks a lot simpler than what we're dealing with here, but this is actually the same kind of thing. So I'm going to get all the dy over dx's on one side, minus, remember that's one big honking term, and all the non-dy over dx is on the other side, so 6y minus 3x squared. Don't lose sight of the goal, my friends. This is where we're trying to end up down here, dy over dx. So we got all the dy over dx on one side, all the non-dy over dx is on the other side, but this is what we're solving for. Whatever shall we do? And the magic answer is factor out your dy over dx, and you're left with 3y squared minus 6x. Nobody said this was going to be pretty, although I think it's beautiful. Our last step then is to just divide, because this is a multiplication problem, and this is the variable we are trying to solve for, so divide both sides by that. So this guy stays in the numerator, and this goes in the denominator. And like I said, this is still our slope function. It's just that instead of having just x's in it, it has x's and y's. So if there's a point of interest, you would plug in the x and the y to get your slope. I hope that helps. The assignments are all on my teacher webpage. Bye.